Previously, we saw that if we have an ST flow and there's an augmenting path, we can use the augmenting path to obtain a flow with larger value. We're now going to look at what happens when there's no augmenting path. And we want to show that the ST flow that we have is of maximum value. And for that, we need the notion of an ST cut. A subset of the arcs C is an ST cut if there exists a subset of the nodes R such that S is in R and T is not in R, where C is given by the set of arcs with tail in R and head not in R. For this directed graph here, if R is the set S comma A, then C given by the set of arcs with tail in R and head not in R, we have the arcs AT and SB. So the claim that we're going to use is that for any ST flow, its value is at most the capacity of any ST cut. And the capacity of an ST cut is simply the sum of all the capacities on the arcs in the cut. So we're going to prove this claim. And to do that, we'll first prove the following. Let R be a set of nodes with S in R and T not in R. Then the value of an ST flow X is given by the sum of the flow values on the arcs in delta plus R minus the sum of the flow values on the arcs in delta minus R. Remember that the value of the ST flow X is defined to be this with R being the singleton node S. So this is a more general way of referring to the value of the flow. And let's see why this is true. What we're going to do is we add up the following. So for each node in R that is not S, we take its flow conservation constraint, which is precisely this. And for the node S, we take this identity. Basically, this identity says the value of the flow is equal to the value of the flow. Now, if we add up all these, the right-hand side will simply be the value of the flow. And we hope that the left-hand side will be precisely this. Let's see what this is saying. If this is our set R, this is the sum of the flow values on arcs that come out of R. And this here is the sum of the flow values on the arcs going into R. If we look at the node V, so that there is an arc with tail V and head not in R, then the variable of that arc will have coefficient 1 in the flow conservation constraint at V. And if I have node U in R, such that there's an arc with U as head and tail outside of R, then there will be a coefficient of -1 on the variable for this arc. So if we add up all these, we'll for sure get these terms. But what about arcs with head and tail inside R? Well, the variable for this arc will have coefficient 1 in the flow conservation constraint at the tail and a -1 in the flow conservation constraint at the head. And so they cancel out. So all we are left with are the variables on arcs that either come out or go into R. And that gives us this. So why is this claim true? We know that this is at least 0. And this is at most the sum of the capacities on the arcs in this ST cut. So we can say that this is at most the sum of the capacities on the arcs in the ST cut, given by delta plus R. But we know that this is precisely the value of the ST flow, and so the claim follows. So now that we know that any ST flow cannot have value exceeding the capacity of any ST cut, in order to show that some ST flow is of maximum value, what we can do is that we can find an ST cut that has capacity same as the value of the flow. And it turns out that we can always do that. So let's see an example on how to construct such a cut. Let X be an ST flow so that there's no augmenting path. And the example we'll use is the following. Here, the arc capacities are given by the numbers in black, and the flow X is given by the numbers in red. And its auxiliary digraph looks like this. And we can see that there's no directed ST path in this auxiliary digraph, so there's no augmenting path with respect to the flow. We're going to let R be the set of nodes V such that there is a directed path from S to V in the auxiliary digraph. And clearly, S is in R and T is not in R because we know that there's no augmenting path, so there's no directed ST path. The claim is that if we take delta plus R to be our ST cut, the value of the flow is going to be equal to the capacity of this ST cut. So this is what we need to check to prove this theorem, but let's see that this is true on this example. Here, the set R will consist of S, A, and B, because we can reach B through the directed path S to A and then to B. And the capacity of the cut given by delta plus R is the sum of the capacities on the arcs AT and BT, is 2 plus 1. And that's precisely the value of the flow. So why does this construction work? Let's say this is my R, and let's look at an arc coming out of R. We know that there's a directed path from S to U in the auxiliary digraph by the definition of R. So in the original network, the flow value must equal to the capacity on this arc, because we cannot possibly have this arc in the auxiliary digraph. Otherwise, the node V would have been included into R. And similarly, if we look at an arc that goes into R, the flow value must be 0. Otherwise, we'll have an arc UV in the auxiliary digraph, and so V would have been included in R. So this shows that the sum of the flow values on arcs coming out of R minus the sum of the flow values on arcs going to R is given by the capacity of the ST cut minus 0, which is precisely the capacity of the ST cut. And remember that this, according to our proposition, is the value of the ST flow. And so we have found an ST cut with capacity that matches the value of the ST flow. And we can summarize this discussion with the following classical result called the maximum flow minimum cut theorem. The theorem states the maximum possible value of an ST flow equals the minimum possible value of an ST cut. At first sight, this theorem doesn't seem very profound, but there are quite a few interesting applications that follow from this theorem.